This exercise is related to ray and the wave diagrams. In this session, we'll discuss how we can complete the ray diagram or the waves for different phenomena. So figure 7.1 shows a side view of an object at the bottom of a tank, and the light travels slower in a liquid. On figure 7.1, draw two rays from the object into air and use these rays to locate the image. So what happened? Because when the light in liquid, it is traveling slower, but when it travel in air, the speed of the light increases. As the speed of a light increases, what will happen? Like if we draw the imaginary line, which is a normal, so it will bend away from the normal. So this light ray will bend away from the normal. Same thing, another ray. When we draw the normal, the red line is representing a normal. So moving from air to glass, moving from liquid to air, again, the speed of the light increases. As the speed of the light increases, it will further bend away from the normal. So it will bend away from the normal and it enters the eye. How this image is seen by the eye? Because our brain always sends that the light is coming straight from the object. So when our brain relocate the position from where the light rays are coming, because our brain always consider light is coming straight from the object. So when our brain relocate the position of the object, the new position of the object is refers to the image. So it will appear closer to the surface. So the two light rays which are in the liquid moving from liquid to air, it will bend away from the normal. As we are looking at these two light rays, our brain senses that the light is coming straight from the object. So when it produces these two light rays backward, the point where the two light rays intersect, our imagination is creating these two light rays and producing it backward. That's why this image is a virtual image. In reality, it is not there. It is just virtual because it's our imagination which create this image. The question, the figure shows a convex lens. The object is there, which is placed between the focus. On figure 7.2, continue the path of these two rays. The distance dimension, continue the path of these two rays for a further distance of 5 centimeter, and using your answer to B1, find and mark position. So how we can work out? We have to continue. If a parallel light ray is there, from where it will pass through, a parallel light ray will always pass through focus. We'll continue to for 5 centimeter, and one which is passing through the center of the lens will pass straight. We'll again continue for 5 centimeter. Then these two light rays will never intersect, and it is obvious that the object is between the focus and the lens. So the two light rays will never intersect. So how we can identify the position of the image? So when we are looking from this side, this is basically a convex lens acting like a magnifying glass. So when we are looking from this right hand side, our brain senses that light is coming straight from the object. So when our brain relocate, extend these two light rays, so the position or the point where the two light rays will intersect, it should be a straight line. Using a ruler, you will draw these lines. I was just showing the idea. So when you extend these two light rays backward, the position, the point where the two light rays will intersect, that is a position where the image is formed. And what are the characteristics of this image? It is magnified, it is upright, and it is virtual, imaginary. It cannot be seen or taken on screen. So whenever object is between the focus and the lens, the image formed by a convex lens is always a virtual image. In question 3, figure 7.2 shows a plane mirror. An object is there, an observer eye. On the figure, draw two rays from the object which are reflected to an observer eye, and then complete a drawing to locate the position. Again, the similar idea that the two light rays which are from the object strike the surface and follow the reflection, law of reflection. These two light rays, again, they will not intersect the two light rays by themselves. So whenever brain sense, it always create, like to locate the image, it will produce these two light rays backward. So as a result, these two light rays will be produced backward. The position where the two light rays will intersect, that will be the position of image. And remember, in a plane mirror, the object distance and image distance should always be equal. Like what distance is there between the object and the mirror, same distance will be there. So best way to complete this drawing, instead of drawing the rays first, instead of drawing the rays from the object, how to do it accurately? What you will do, you will measure the distance from object to the mirror. Like example, if this is 2 centimeter, using a ruler, you will measure this distance from object to mirror, and same distance you will make other side, because we know object distance and image distance is always same. Now what we do, we'll draw two light rays from the image, directly from image to the eye. And we just join these two light rays from object to the mirror. So this is how the image is formed by a plane mirror. So two light rays bounce back after striking a mirror, enter the eye. So when the brain sense, it produces them backward. As a result, we'll see the image. So best way to complete a ray diagram, whenever you have a plane mirror, always draw the image first, like mark the position of image and continue the rays till the eye, and then draw the rays from the object to the mirror to complete this figure. And figure 7.1 shows an object and its image formed by a converging lens. So whenever object and image are on different sides, so this will always be a real image. And you can see real images are always inverted by a convex lens. So the question is, place a tick in all the boxes, correctly describe image. So when you compare the size of object and size of image, so image appear to be smaller, so image is diminished. Smaller means it is inverted, that is true. And it is real images are always inverted, so this is always a real image as well. If it was a virtual image, it will form on the same side, it will be upright, and it will be enlarged, or you can also say magnified. Figure 7.1 shows a ray of a light traveling in an incident on a glass prism. Critical angle is 42. On the figure 7.1, draw carefully without calculation and continue the ray. So how will continue? First, because it is passing along the normal, like this is the direction in which ray is coming. So that direction is same as the direction of the normal. So if ray is passing along the normal, it will pass straight. So when I draw this normal here, so it is passing along the normal, so then it should pass straight. Now, when it strike a denser to rarer boundary, we'll have to draw. Always whenever strike the boundary, draw the normal. Normal is always 90 degree or perpendicular to surface. So you'll draw a normal. Then identify what angle is this. Look, if this is 60, this one is a 90. So this will be 30. And if this one is 30, what will be this angle? Because total angle sum of a triangle, that is 180. So this is 30. So remaining of this angle will be 60. Because total is 90 between the normal and surface, so this will be 60. So if this angle is 60, now this angle is now the incident, and this angle is more than the critical. If angle of incidence is more than the critical, then there will be a total internal reflection. Means all of the light ray reflected back in the same medium. So what will happen? It will reflect back in the same medium with an angle of 60 degree. So it will bounce back here with the same angle of 60 degree. And then again, we'll draw a normal. Always, whenever the rays strike a boundary, air to glass, air to water, whenever it strikes a boundary, we will always draw a normal. Now, as we can draw a normal here, so this angle appear to be smaller. So the angle of incidence is between the normal and the incident. So this was the incident. This is appear to be less than the critical. So if it is less than the critical, what will happen? Moving from glass to air, so it will bend away from the normal and the speed of the ray will increase. Another question, a source emit a visible light. Figure 6.2 shows a ray of a red light from a source incident on face XY. On figure, draw the refracted ray and emerging out at face X and Z. So what will happen? And a ray of a blue light follows the same path as red. So first one is on figure, draw a refracted ray at a face and ray emerged out and label that as R. So first one is red. Moving from air to glass, it will bend because it slow down. So this is, if it does not change the speed, it will pass straight. If it speed up, it will bend away from the normal, but because it slow down, so it will bend towards the normal. And then we'll draw another normal on the face X and Z. So normal is always perpendicular to surface. So it will bend away from the normal. And now they're saying there's a blue light enter, as we know, violet, indigo, blue, green, yellow, orange, and red. The violet is having the highest frequency, will bend the most. So this will bend the most and red bend the least. So there now we have to complete a path for a blue light. So blue will bend least. So roughly we'll sketch and it will bend away from the blue will bend most, red bends the least, so blue will bend the most. If there was a violet, then it will be further down. So according to the frequency, we can identify which one bends the most and which one bends the least. In question 7, figure 7.1 shows a parallel wavefront. We have to draw a position of 4 reflected wavefronts and draw an arrow to show the direction and label the angle of reflection. So how to work out this? This is the direction in which the ray is passing. So imaginary line, because reflection is there, in reflection, angle of incidence and angle of reflection are always equal. So this is the imaginary line which is perpendicular to the surface, we call normal. And in a reflection, the angle of incidence will always be equal to angle of reflection. And then drawing the wavefront. Wavefronts are always perpendicular to the direction of the wave. The blue arrow is representing a direction of the wave. So wavefronts are always 90 degree or perpendicular. So this is how we draw the refracted wavefront and label with an letter R the angle of reflection. So this one is angle of reflection. This is the direction in which the ray is going, and these are the reflected wave fronts. Another similar question, figure 8.1 shows a parallel wavefronts of a light which is in ice and moving from ice to air. The speed of the light is 3 into 10 power 8. So 3 into 10 power 8. So it means the light travels fast according to the value. In ice, it is traveling at a slower speed. In air, it is 3 into 10 power 8 meter per second. So speed increases. When speed increases, it will bend away from the normal. Draw the wavefronts as it is passing. Draw an arrow to show the direction in which the refracted ray will travel, and label the angle of incidence and angle of reflection. So how to do this question? First, always you will complete an arrow to show the direction in which the waves strike. Then draw the imaginary line which is perpendicular to the surface. We call that as a normal. Because it is moving from ice to air, so in air it is traveling faster. If there was no change in speed, then it will travel straight. If it's slow down, then it will bend toward the normal. But because as the question they mentioned speed up, so it will bend away from the normal. And then we have to draw the wavefronts. So how to complete a wavefront? The wavefronts are always perpendicular to the wave. So this is the direction of the wave, direction in which the wave was traveling. So how to draw the wavefronts? Always perpendicular, because this is the direction in which the wave is refracted. This is a refracted ray. The direction of the refracted ray and the direction of the wavefronts are always 90 degree. So we'll draw a perpendicular like all, and the wavefronts in air should be parallel to each other. So we are drawing the parallel lines, the wavefronts. So here what happened, the speed is increased, the wavelength also increased, but the frequency remained unchanged. Then we have to label the angles, the angle of incidence and angle of refraction. So the angle of incidence with the letter I, angle between the direction in which the wave is coming and the normal, and the angle between the direction in which the refracted ray is going and the normal, that is angle of refraction. Figure 6.1 shows a crest of a water wave moving from left to right of a harbor. On a figure, draw 3 more crests. So this is basically a bending of the wave around the obstacle, that's called diffraction. So when it passes, draw the 3 more crests to the right of point A. So A is this. So what will happen? This part will not diffract, only the part which is near the edge will slightly changes the direction. And during a diffraction, the wavelength does not change. So we have to keep in mind, like if this distance is say 1 centimeter or 2 centimeter, we should keep 2 centimeter distance and draw the wavefronts. Because this is the edge, so near the edge, the waves spread out and we call that as diffraction. If we were having a gap like top and bottom, both sides, there were edges or barrier or obstacle, then we'll draw circular wavefronts. But because only one side barrier is there or there's an edge, so the diffraction will occur, only the waves spread out only in one way. Then figure 6.2 shows crest of another wave moving from left to right in different parts of a harbor. This wave moves from deep to a shallow region, as you can see. On figure, draw an arrow to show the direction of movement of wave after it has. So remember, the direction of the wave and the direction of the wavefront are always 90 degree. So we'll use a compass, and this is a wavefront. Any one, it's not necessary. You can take any of them. I can take any of them, and the direction, I can take this wavefront, I can take even the first one, any one of them. So direction of the wave and the wavefront, always remember they are 90 degrees to each other. The angle between them is 90. So this is a wavefront. So the direction in which the wave travel will always be 90 degrees. In this question, figure shows a green light which is passing, a red light enters, complete a path for a red light. So we have violet, indigo, blue, green, yellow, orange, and red. Red will bend the least and violet will bend the most. So we have a green compared to green. Red will again bend the least. So when we want to complete a path, we will show refraction, but at a smaller angle deviation, and then complete the path. So same path, same trajectory is there, same pattern. Like first it bent towards the normal and then away from normal, but bending of a red should be least as compared to violet, because violet bends the most as it is having the higher frequency, so it changes speed more than red. Another question, figure 7.3, draw path for a red light. Which light is this? On figure, draw the path. Figure 7.3 shows a green light. So this is a green light. Again, we have to complete for red. So same idea, when it moves from air to glass, it will bend, because this is a bending toward the normal, so it will bend less and then away from the normal also. So this will be the path for the red. Because green is already done, we have to complete the path for red light. Red bends the most. Violet bends the most and red bends the least. Figure 7.1 shows a converging lens and the image is shown. An object is placed on the left of the lens. The principal focuses are labeled as A and B, and the lens is labeled as C. On the figure, draw rays, locate the position of object. How we can locate the position of object? First thing, from object, if there is a parallel light ray, from object, if there is a parallel light ray, from where it will pass? It will always pass through focus. So if we relocate, like one of the light ray which is passing through the focus and one of the light ray passing through the center of the lens will pass straight. So these are the two light rays. So how to locate the object? We just produce, because if it is a parallel, it passes through focus. So if I use different colors, so one of the light ray which is passing through focus after refraction, refracted from the lens, another one from tip of the object passing through center. So this light ray which is passing through the focus, it means it should be parallel to the principal axis. And the one which is passing through the center of the lens means it was passing straight. So when we locate this position, so this appears that the object is at this point. This is the position of object. So using an image position, we can locate the object. First, the parallel light ray will pass through the focus, one through the center of the lens will pass straight. And the position, the point where the two light rays intersect, that is the position where the image is formed. So from position of image, we located the position of object. Then bring the following distances equal to the focal length. So which distance is focal length? Focal length is a distance C and B. Then object is shown. Figure 6.1 shows a full-scale diagram of a converging lens. Two principal focuses, f1 and f2, and the object is there. On figure 6.1, draw two rays from object, determine the position of image, and label that as ij, and measure the length of image. And three. So first, what happened? the parallel light ray. Remember, whenever object is between the focus and lens, image will always be a virtual. So first parallel light ray, it will pass through the focus. One through the center of the lens will pass straight. So these two light rays will never intersect because the distance is increasing. So when we look from here, when we look from this side, our brain sense light is coming straight from the object. So when it recreate the position of the two light rays, produce them backward, the point or the position where the two light rays intersect, our imagination only created this image. That's why it is a virtual image. So the point where the two light rays intersect, that will be the position of image. It will be somewhat here, but because I'm not using a proper measurements ruler, that's why I'm getting a bit far from the principal axis. So, but it will be somewhat within this region. Then you have to use a ruler, measure this height, using your scale, measure this height. Then 3 description. Is it diminished? No, it's not. It is magnified? Yes. Is it real? No. Same size? No. Same way up as object? That is correct. Because if object is up, image is up. If object is down, like it, we can say it is upright. And it is uh, upside down compared to object. This is not inverted. Like if object is letter A, it will be same letter A but magnified. And is it virtual? Yes, it is virtual. So magnified, virtual, and same way up as object, or we can say upright image. So image formed by a convex lens as a magnifying glass, when object is between the focus and the lens, it is always a virtual image. Then this question shows 3 rays of a green light passing through the glass block. 3 rays of a red light approaches a glass block for a same. On figure, we have to sketch a path for these red light. So green light is there, but red will bend the least. So the path which red will take, green will bend most, red will bend the least. But the one which is passing straight will go straight because it is passing along the normal. So that part of the red light, when it is passing, it will go straight. So these 3 light rays, when they intersect, they will intersect far away from the object. So this is how we complete a ray diagram. So always remember, violet bends the most and red bends the least, because violet is having the greater change in frequency, a greater change in speed, not frequency, as compared to that of red. Figure 5.2 shows a crest from a point source approaching a straight barrier. On figure, indicate and label one wavelength. Wavelength is the distance between two successive crests, or the distance between two successive wavefront is also known as wavelength. So that is lambda. On figure 5.2, draw 3 crests. So when the wavefront they strike, so this will be reflected one we have to draw. So when it bounces back, these are the 3 reflected wavefronts. As the waves strike the barrier, the wavefronts bounce back. Figure 6.1 shows the wavefront of a light crossing the edge of a glass block. Draw incident, normal, and the reflected meet at same point. So we want incident. How to draw the incident? As I mentioned, the direction of the wavefront and the direction of the wave. So direction of the wavefront and the direction of wave are always perpendicular. So this is a wavefront. So what is the direction of the wave? So this will be the direction of wave. And we have to show a point where all the three can intersect, like three are will meet. So we'll draw perpendicular, a line which is perpendicular to the incident. The red line is perpendicular to incident. That is an incident ray. Then imaginary line, which is perpendicular to the surface, we call that as normal. So the one which is 90 degree to surface, that imaginary line is a normal. And then what happened? The refracted ray, how to draw a refracted ray? The one which is perpendicular to the refracted wavefront. So these are the wavefronts, so refracted wavefront. This the same ray. I can use another color. Example using black here to show the direction of the refracted. As you can see, the angle between the refracted wavefront and the refracted ray should be 90. The angle between the incident wavefront and the incident wavefront should be 90. An imaginary line which is perpendicular to surface, we call that as normal. And we can label angle of the incidence, angle between the incident and the normal, angle of incidence, and angle between the normal and the refracted, that is called angle of refraction. And because the speed of the wave decreases as it approaches the barrier, that's why the angle of refraction is smaller than angle of incidence. So label and then measure the two angles using a protractor. You have to measure these two angles and write the answer here. At Q, some of the light is reflected and some is refracted. Draw the approximate path. Because it is some of the light is reflected, so it will follow law of reflection. It will be 30 degrees. And some of the light is refracted because moving from air to glass, moving from glass to air, speed increases. If speed does not change, it passes straight. If speed decreases, it bend toward the normal. But speed increases, so it will bend away from the normal. So we have to label whenever you complete the ray diagram, label. So this is a refracted and this one is a reflected. So these are some questions related to ray diagram.